Hello and welcome to C++ Weekly. I am your host, Jason Turner. In this episode, I want to talk about C++ 26's expansion statements, which you might also know by the name of template 4. Before I get started, I do want to remind you that I've got a swag store up and I've just put up a bunch of new designs that, well, I had fun putting together anyhow, and I don't know if anyone else will enjoy them, but I'm hoping that you will at least check them out. There's also the classic designs for maybe unused, no discard, const expert, etc. First of all, I do want to point out to you that these expansion statements have been merged officially into the C++ standard, and you can go and check them out in the current draft standard of C++ 26. There's a lot of rules here about what they can do. They're either going to do like a ranged for loop kind of thing over them, or they're going to do a destructuring statement. So notice here it does support in the form of begin and end. And we're going to have to play with that a little bit more because in my experimentation I was unable to get that to work. But I can show you the basic ideas of how this works and how you can use it. Let's start with the fact that I am currently using GCC trunk, and I am going to put this in C++ 26 mode. Let's start with what I think should be the most basic use case of where you might want to actually do something like this. Of course, if I just try to do a ranged for loop over the values of this tuple, I'm going to get this compile error that begin and end cannot be found, because ranged for loops need to work over a homogeneous set of things. This val here must always deduce to being the same thing. This is where template 4 comes into play. And this allows val here to be a different thing on each loop iteration. Now, let's go ahead and enable some optimization. And this code's going to go away. We're not doing anything here. See the call to get tuple. That has been not defined. And again, I'll remind you, this is an absolutely spectacular way of working with Compiler Explorer that you declare but not define as many things as possible so you can get some idea as to what the compiler can do when it doesn't have full visibility into your code. I'm going to go ahead and write a little use function. Now, I didn't test this when I was preparing for this episode, so we're going to see what exactly this does. Unfortunately, yes, we're going to see implicit conversions happen all over the place. So I can see that the use with a double version is being invoked 3 times. Let's go ahead and provide an int overload for this. I'm hoping, no, I didn't get an ambiguous overload, unfortunately. That's all right. So I'm seeing that I'm getting the use int working for the int member of the tuple, and then again for the car version, and then I'm getting the double. Let's go ahead and provide all 3 overloads. And let's make sure that we enable our conversion warnings and turn on errors so that we don't get this kind of error again. You can see that the compiler has been able to, well, unroll is a very strong word here. It's not really unrolling the elements. It is forced to make 3 separate calls here. It's not the same thing as loop unrolling. We can see that we can basically visit the members of a tuple very, very simply. A tuple is something that can be destructured. We see this with structured bindings all the time. So we might do something like this. The template 4 now works in a very generic way. I can write a function that takes anything that is destructurable and visit each of the members of it. So now I have a function that is returning an element of this data type that has a car, double, and int and an int. If I update this, to do get data, then I am going to see the calls to those 5 members in here, car, double, and int. And it's going to walk over those things in the order of declaration because we've got this structured binding that is possible from a plain old data type or a standard layout type like my data class here. This is frustrating that it won't let me introduce this structured binding outside of a template context. So let's go ahead and make a quick template function. This template 4 is kind of the moral equivalent of this use data here. But this is only possible because C++26 allows us to introduce an expansion pack in a structured binding. It's kind of neat to see all of these things coming in at the same time, but also a little unfortunate that we have to wait until C++26 to get any of them. All of this is handy, but this isn't the real strength of this tool, I don't think. The real strength really comes when we want to work over constant expressions. Let's go ahead and declare a new getData thing. It did take me a minute to fully understand the requirements and syntax here, so hopefully this will make sense as I explain it to you. If I wanted to simply do a loop over the values in the get constexpr data, and just to illustrate my point, I'm going to make this const-eval to force the evaluation of this function at compile time. Now I'm going to do something like this. Something that requires a constant expression. And I'm just going to call this use constexpr. And again, I'm just forward declaring this function. This is perfectly fine. I can forward declare templates. If I want to call use constexpr val here, this is not a constant expression. It doesn't pretend to be a constant expression. It's a const auto reference into something that we know was evaluated at compile time, but still not a thing that is actually constant expression. The syntax here will let me do something like this, constexpr auto val. That is valid, but now I get this anonymous is not a constant expression. So I'm not allowed to do this constexpr looping over the elements of a temporary that was returned from this function. So let's go ahead and move this out here. If you're following along at home, you might predict that this is still going to fail to compile, but we get a more explicit error now. Data is not a constant expression, and that is fair. Let's go ahead and make this a constant expression. Now we're going to get a different error. Reference to data is not a constant expression. Oh, you're right. The reference to data is not a constant expression. Let's remove the ampersand there. I'm still getting that same error. Reference to data is not a constant expression. Okay, I am basically forced to make this constexpr static data. Fine, I have constexpr static data, and now I can see that it is actually pulled out and invoked this function 5 times at compile time with the constant expressions that were in the data thing here. Great. Now, there might actually be some argument to making this a reference, possibly. I don't know, might remove some of the compile time overhead. I'm not sure. Of course, C++20, I believe, introduced 4 init statements. So I can do this. I can declare that data thing right here cleanly inside of my template 4 if I wanted to. And I'm not even going to bother doing it for the sake of this example here, but if you're bored, I want you to attempt to write the exact same code that can do a constexpr loop over a constexpr structured binding thingy. You basically can't do it before C++26. I did point out that this was looking for a begin and an end. or at least it can according to the spec. So let's go ahead and get a standard array. And then we'll decide if this is a limitation in GCC's implementation or if this is a limitation in our understanding of this feature. I'm just going to get an array of 5 elements, and then I'm going to do a template for over the result of this array. This should work. The standard ease that we were just looking at says that it can look for begin and end here. But I get a call to non-const expr function, standard array get array. Okay, let's make this a const expr function. And let's just return 5 elements. Okay, that actually worked. I don't know why this required a const expr function for begin and end. Yeah, I don't understand. I don't understand why that should require a const expr function. That doesn't make any sense to me. Let's go ahead and data cannot bind to a temporary of type data. Non-const L value reference. Non-const L value reference to type data. That is not a non-const L value reference. In fact, let's try doing a copy here. Okay, that fixed that. And let's try getting rid of the const expr on get array. And we'll just see if there's perhaps some confusion about what exactly is required here in our compiler implementers. Yes, I would say this counts as some level of confusion. So in theory, we get something like looping over structured binding elements, because that's generally what it's doing, is a structured binding. Some sort of looping over constant expressions, which is spectacular. And then I'm going to call this something like forced unrolling of ranges. Oh, that might be why GCC thought a const expr function was required there, because it needs to know the size of the thing at compile time, but with standard array, it knows the size of the thing at compile time anyhow. So I don't think that that's a valid argument. Well, anyhow, I hope you enjoyed this episode of C++ Weekly. This is clearly a little bit still in flux, but a very, very powerful tool and necessary for the next episode that I am getting ready to record. So thank you for watching this episode. Be sure to subscribe, and I will catch you next week.